Why are we here? What's the origin of life? Why the properties of the universe are the way it is still a quest.
The 30-meter telescope will allow us to understand each and every one of these questions.
The primary mirror is 30 meters across. So that's 3 times the diameter of the current largest telescopes.
At that scale, it's virtually impossible to build a single piece of glass. So the way we will achieve this size is through segments.
TMT builds on the heritage of the Keck Observatory. The Keck telescope was the first segmented mirror. The mirror itself is made up of 36 segments that all lock together to make a single surface.
30 meters is roughly 400 segments. It's big enough that you can make the next leap in terms of our understanding of the physical universe, while not being so big as to be unbuildable.
It gives us very sharp views of the distant universe. There's been great progress over the last 10 years in a phenomenon which we call adaptive optics, which allows us to correct for the blurring in the Earth's atmosphere.
The trick to this is to shine a laser into the atmosphere and to watch the spot to tell us how that atmospheric distortion is happening.
So the correction effectively takes out the twinkling of starlight and renders them as very sharp points of light. It means we not only can see fainter objects, but we can actually see details much more clearly than we would ever have been able to before. The Hubble Space Telescope has definitely set a milestone in high-resolution imaging. We've all seen beautiful pictures of distant galaxies. TMT, with adaptive optics, gives us a much finer quality of detail than Hubble Space Telescope. Hubble is about 2.5 meters across. TMT is 30 meters across. So we have that ratio, a factor of 15 or so, improvement in image quality, plus the bigger aperture that enable us to see fainter details. So you're impressed with Hubble? Wait till you see TMT. When we look deep in space, we're looking back in time. And so what I'm trying to do is, in a sense, build a picture book of how the universe has evolved from its beginnings to the present day. The 30-meter telescope will allow us for the first time to understand when did the very first galaxies and stars switch on in the universe.
The big challenges in astronomy is to be able to detect Earth-like planets around stars other than the Sun. And this to date has not been possible. And with the 30-meter telescope, we should be able to detect an Earth-like planet and to take spectroscopy of this planet to understand the potential for life elsewhere in the universe.
90% of the material in the universe is dark. We don't see it. The 30-meter telescope will allow us to look at the structure of dark matter. If you like, its granularity. Is it smooth? Is it lumpy? On very, very fine scales. TMT, in studying dark matter, will actually complement laboratory experiments trying to detect dark matter, for example, at the Large Hadron Collider in Geneva. So TMT is an enormously powerful science instrument that's part of the armory of the physical scientist over a wide range of wavelengths and even disciplines. It's 400 years since the telescope first was invented, and it's been an astonishing story of scientific discovery. And the 30-meter telescope will extend and continue that story in a dramatic way.
name is Brian Smith. Welcome to the TMT Technical Lab. Here at our TMT Technical Lab, we run many tests daily. Some of the tests, now that we're finished with our M1 FDR, we're preparing for production here at the lab. Some of these tests that we're running currently have to do with our MCP that you see behind me, our multi-segment test bed. Further on in the lab, we're also getting prepared to send our SSA out for an important optical test. So this is our primary mirror segment support assembly, also known as our SSA. It's comprised of 27 fingers, if you will, to support and also minimize sag along the surface of our thin segment. The fingers, if you will, are also known as our mirror rod flexors. So there's 27 of these guys along the bottom. Also, this segment that you're looking at here was successfully assembled here at the lab with our Indian colleagues. And this will be the first production parts that will actually enter the telescope.
In this activity, you'll model and measure the collapse of a large star to understand the important role of density in black holes. You'll need a latex balloon blown up to 6 to 8 inches in diameter, a few sheets of aluminum foil, a digital scale, a flexible tape measure, and a pair of scissors or another sharp implement. Completely wrap the balloon in the aluminum foil. When you're done wrapping, you don't want to see any of the balloon peeking out. It may take a few sheets of foil to do this, depending on the size of the balloon, so use whatever you need. This foil-wrapped balloon represents a large star. Measure the circumference of the balloon with the tape measure and weigh the balloon on the scale. Record your baseline measurements. Gently squeeze the balloon. Here, you are the giant hands of gravity, and the balloon should resist being squeezed because of the air pressure within the balloon. This is similar to what happens during the normal life of a star, when gravity is balanced by fusion energy created at the core of the star. Now you're ready to simulate the end of the star's life as it runs out of fuel and that balance is broken. Pop the balloon carefully, trying not to crush the aluminum foil as you pop it. Be the hands of gravity again, and gently squeeze the aluminum ball. This time, it doesn't push back. Make it about an inch smaller, keeping it as round as possible. Again, measure its circumference and weight and record your new measurements. You'll repeat those steps a few more times, crushing down the foil ball about an inch more between measurements. For your final measurement, crush the ball as much as you possibly can while keeping it round. Take one final measurement of its circumference and weight. You'll see that even though the size of the ball changed, its mass did not. This means that it just got more and more dense, like when a star collapses into a black hole.